Hi, I am Guille, and I'm here to talk about testing finalization mechanisms with Heap fuzzing. So this work is, so I'm working in INRIA. I have a first slide to give a quick introduction about myself. So I am a researcher at INRIA Lille in the north of France. I did my PhD on reflection, developing system dynamic updates and stuff like that. Right now I work a lot on compilers, testing, test generation. So soon I hope to have to be working on benchmarking and automatic benchmark generation and stuff like that. So here is my email if somebody wants to contact me. So I am eager to discuss and talk about this kind of stuff with anybody. So this is the paper I'm going to present today. So testing finalization mechanisms with heap fuzzing. But this paper it started actually with a really concrete motivation, which was debugging the ephemeral implementation in the Faro virtual machine. Yeah, so it was actually when we started testing the ephemeral implementation, it was a bit hard because testing garbage collection implementations is not straightforward, and there are some things that actually make it even more challenging. So the first thing is that most of the garbage collection bugs will show themselves as memory corruptions. So what will happen is that you will see the symptom, that is the corruption, and which will be very far away from the cause in time and space. What do I mean by that? So I mean that first maybe it happens a couple of seconds after the corruption actually happened. So you see the cause, the symptom, maybe sometime later, and you see many and not in the same place where actually the cause happened. So when you see the bug, you have no clue of when actually the problem appeared. And this is even worsened because it is masked by side effects, because the program continues executing and many things happen in the middle. So maybe the corruption actually was overridden by some other stuff, or even it was propagated over the system. So that makes debugging garbage collectors much more complicated. So two main causes of such corruptions are, first, use after free errors. So this is from the Chromium project. The Chromium project identifies that 70% of high severity issues are right now, even today, memory corruption issues. Yeah, and most of them are use after free. What are use after free errors is that you allocate some memory, you free it, and then you try to use it, but you already return it to the system. So maybe that memory is not yours to touch, or maybe it has been reused, and so the memory, it has not the values that you expect. Yeah. So this is one of the possible problems that can happen. The other problem that can happen very often is the expire pointer dereferences, which means that you are referencing an object that maybe it was moved or invalidated. So this is something that will happen, for example, with moving or copying GCs. So that will actually copy objects around in the memory. So the object is somewhere in the memory, but it's not where you are expecting it. So for example, here you allocate some object and you move it around, and then if you want to use it using the old reference to that object, that reference is actually old. Yeah. So you have to take really care of using the correct reference, which is the moved one. So an extra challenge are ephemerons and weak references, because they add a lot of subtle GC bugs because they complexify memory traversals and markings. So for example, ephemerons, which actually comes from, so the paper from that introduces ephemerons is from 1997. Ephemerons are just a mechanism to introduce a finalization, efficient finalization. And actually, the implementation of ephemerons requires that the garbage collector identifies ephemerons on the traversal and queues them for later processing. So actually, you have a processing of objects in 2 or 3 phases, and that actually adds a lot of potential bugs there. So we started to think how do we efficiently test garbage collection algorithms? Yeah. And instead of how do we test garbage collection algorithm, actually my idea was how do we create inputs automatically? So how do we fuzz? So that we exercise the garbage collector algorithms. And the idea is that it's not to just fuzz and create random inputs, it's to create inputs that are intelligent enough to detect problems. Yeah. So yes.
Sorry, yeah, one question. So we are
Yeah.
only seeing your first slide, the title one.
Oh, that's a problem. Probably. So I have been moving slides. What do you see there?
Now we see first about me. Yeah.
Now it moves.
No, it doesn't.
So I have a problem with the presentation stuff. I will share the entire desktop, and you will tell me.
Okay.
What do you see now?
We see the paper, some GDP maybe.
Okay, now it moves. Yes.
Okay. Yes.
Okay.
Yes.
So, okay, I'm sorry. I should have tested that. Okay, so here I was talking about the ephemeron testing, garbage collection bugs, use after free errors, expire point in the references. I can do it again later if you want to for the recording. We can arrange that if you want. So I was here, yeah, fuzzing. Yeah. So, so how do we test garbage collection? So we started looking at the spectrum. So how different ways of fuzzing. The typical way that people use right now to fuzz virtual machines and language implementations is the way in the right. So it's a more high level. So it's to automatically generate programs that will execute on top of a virtual machine and exercise some part of the virtual machine. Most of the work there is to test JIT compilers. So they try to create patterns, so code patterns that will make the JIT compiler do something that maybe has a bug. Yeah. On the lowest level, one other idea could be to, for example, to just create a memory with random values, and maybe not so random or random, smartly chosen random values that. And then we run the garbage collector on top of those automatically generated memories. Yeah. So on the memory fuzzing, so one of the things that if you think about it, one of the things that happens is that, yeah, we can generate those random heaps. Actually, that could be easy. It's just generating random integers and then put them in some memory. We are fuzzing at the byte level. But the problem is that most of the memories will be invalid for the garbage collector. So they will not satisfy the garbage collector preconditions. We'll find probably a lot of errors, but the errors will come from not from the garbage collector itself. It's because our memory doesn't have objects and doesn't have valid values for the garbage collector. So actually we discarded this approach really quickly when discussing. Then we started to look at what happens with actual real applications. So we want to use real applications to test the garbage collection. And we started to look actually at allocation patterns of different applications. So we ran a couple of benchmarks. So this is not part of the paper, this we did later. And here you see, for example, in the graph that each column is a type of object. So we have normal objects, we have byte arrays, we have arrays, we have weak objects, and so on. And on the y-axis, we have the size of those objects in bytes. Yeah. The dots are bigger. The dots represent the number of objects of this of a particular kind on a particular size that were allocated. So here, what you see is that most of the allocations that we see in the benchmarks that we saw is that most of the objects allocated are small, and when you have large objects allocated, they are actually sparse. So they are actually not exercising a lot of different values. So they are mostly the same. So you have a lot of byte arrays that have 1,000 elements, a million elements, but maybe those values are not interesting for the garbage collector. So what we see is that applications have stable allocation patterns. And that makes that if we think about the garbage collector testing as a search problem. So we have a partial exploration of the search space. And maybe that partial exploration is not exploring the interesting parts of the garbage collector. So that means that since we are partially exploring, maybe that partial exploration is not efficient at finding bugs. It has low probability to hit interesting scenarios for the garbage collector. So, and when we hit one of those bugs in production, it is very complex to reproduce because we had to do a lot of stuff until we found one of those interesting scenarios. Yeah. So how can we improve on this? So the idea that we had was that, okay, we have this spectrum of low level, high level. What if we find something in the middle and we fuzz directly the allocator and the GC API? Yeah. So we have the virtual machine that has already an API that allows us to control, for example, where objects are allocated, what size they are, and so on, and when the garbage collector is run. So when we came with this idea of heap fuzzing, so let's talk directly to the heap, to the allocator, yeah, the virtual machine allocator, and generate scenarios by talking to it. Yeah, and we are not running normal Faro programs or smalltalk programs. We are actually talking directly to the virtual machine. So for example, here in this example, what we're doing is we are taking the heap and we are telling it, okay, allocate a new array of size 20 slots, and it will not be a root object. Yeah. And then we are going to instantiate another object that will be in the old space. So it's an allocate old. It will be an array of size 10, and it will be a root object, this one. And then we mutate the array, the first array, and we make it reference the second array on the first slot. And then we run the garbage collection. Yeah. So the question is, okay, I have this scenario. Did it run okay or did it not run okay? Yeah. So this is kind of the idea. So how does our solution actually work, and how does it detect if something works or not? So let me give you some overview, and then I will give you a nice picture with the ideas. So the idea is that we are fuzzing the GC and the allocator directly, not the application or the memory. Yeah, that helps us in having control and determinism and to create a scenario that makes sense to the garbage collector. The second thing is that our solution is not completely random. We have made fuzzing based guided by experts. Yeah, so the experts, so people that know how the garbage collector works, somehow change the probability of events, and they can add new kind of events. For example, we can have different probabilities of running the garbage collector or allocating objects and so on. So our solution is the overview of our solution is on the right here in this picture. So we have an expert that writes a fuzzer. So we have an expert written fuzzer that will generate events that are highlighted there in red. We're taking a lot of events and putting them on the virtual machine, running them with assertions enabled. And what will happen is that the VM with these assertions enabled, it will either pass, so it's kind of a smoke test, if you think of that, or it will fail in some assertion. Yeah. Once we have a failure, we take the events and this failure, and we reduce the events to remove those events that do not play any role in the failure, and we can debug it with much less events. Yeah. So the kind of events that we are managing right now are mainly of three kinds. So we have allocations, and allocations are configured by where do you want the objects to be allocated. So it will be in the new space, in the old space. It will be a root object or not. What kind of object it will be? It will be an ephemeron, an array, a normal object, a weak object. How many slots do you want for this object, for this allocation? Yeah, so all allocation events are configured like that. Then we have mutation events, where we are going to say, okay, this instance variable of this object is going to now reference to this other object. And then we have garbage collector events. Of course, we can force the garbage collector on the new space, on the old space, or a more aggressive collection and so on. So these are the kind of events. Now we are working on an extension of this paper also that has other different kind of events that, for example, we can target pinning or unpinning and stuff like that, or become. And the idea is that different events can actually guide the garbage collector towards different parts of the code and find different failures. Now, I said that the generation of these events are guided by an expert. So an expert writes a fuzzer. So the generation of events is mainly random, but that random is actually guided. So experts will play with frequency of events and the kind of events mainly. So for example, an expert can say, okay, for testing some part of the garbage collector, I want that allocations are 10 times more probable than garbage collection events. Or you can say, okay, I want that ephemerons are more probable than non-ephemeral objects. I want objects that have less than 10 instance variables in general, so or that are more probable than objects with more than 10 instance variables, and so on. So we can play with this kind of configurations to actually guide the generation of events. And then we have this VM with assertions enabled. So what are these assertions? So we have two kinds. First, we have code assertions that are checking pre and post conditions. Yeah, so in the code of the virtual machine, when the garbage collector is running and when the mutations run, we have a lot of assertions. So here, for example, you have a piece of code that is iterating all the objects in the old space from an initial object, yeah, and doing a block. So it's executing a block for each object that it finds since the initial object. So this is doing, if you check in between the lines, so it is taking the initial object, and then it is until it is at the end of the memory, it will take the next object and the next object and the next object and so on. Yeah, and executing the block for each of the object that is found. In between the lines, you have a couple of assertions. Those assertions are validating that the iteration is healthy, yeah? And those are the kind of assertions that can detect a problem. So if you have an object that is broken, one of these assertions will fail, yeah? And we have a lot of those in the garbage collection implementation. The other kind of assertion that we have are heap invariant checks. So these are more expensive checks that are run after or before each garbage collection, and that do a full traversal of the heap, checking that general stuff, like, for example, checking that all objects have a correct class and that they reference valid objects. Yeah, so they do a full scan and check that, okay, is this heap, it is healthy or not? And then we implemented also test reduction algorithm from Andreas Zeller. So this is the DD-mean algorithm that you will find in this paper here. The idea is to discard all the events that do not contribute to the bug. Since we're generating random events, so they are guided, but there are still there's some random in there. So it may be that we have events that they do not play any role in the failure that we are observing. And so that means that we can automatically reduce them to help in debugging, so to remove noise from the debugging. We evaluated our solution for this paper, asking ourselves actually 3 questions. So first, we ask ourselves if actually this thing actually found bugs or not. How many events were required to hit a bug? And how effective was test reduction in those cases? Our experimental setup was that first, we only wanted to find bugs in the ephemeral implementation. Yeah, for this paper was actually, the experiments that we did were actually focused on ephemerals. We didn't do anything until later, so we have now an extended version that is testing more stuff. I can talk about that if somebody has questions or I have time.
We have like 2 minutes.
2 minutes?
Yeah.
Okay, so so we focused on ephemerals. We did 100 fuzzings and a timeout of 100 events. So to answer the first question, we ran it a lot. So we found that 37 out of the 100 fuzzings that we ran presented a failure. Out of those, we studied them manually, and we found 5 unique symptoms, which were produced by 3 unique causes. So we can say that we found 3 different bugs. And after fixing these bugs, actually couldn't find any hard crash on the virtual machine later, or at least on ephemerals. We also studied how many events were needed to hit a bug. So we generated 100. We can then discuss if this 100 was good or not. But one of the things that we observed is that for ephemerons, most of the errors were actually hit really early, so with less than 50 events. So then we can also say that 50 events was good enough to find bugs with a certain probability. And after test reduction, most of our failures were actually did only have 4 or 5 events, so were super easy to debug. So I have put here, maybe we don't have the time, but I put here the examples of code of those 5 events after writing them in code. So those were tests that were 5 lines of code, 10 lines of code. So they are in the paper if you want to take a look at them. So in general, what you will see is that we found cases where ephemeron classes were collected. Ephemeron values were collected when the keys were strong. And we found also some bugs in the compaction algorithm. So as a takeover, like that, I finish on time. So heap fuzzing looks like a simple and effective model to find GC bugs. Our events were expert-driven and were directed to the allocator, and not we were not fuzzing directly a program or the memory. And if you want more information, the paper has a lot more details. So thank you very much for your attention. And if you have some questions, we have, I think, 5 minutes.
Thank you, Isha. This was very interesting talk. Yeah, so we have some minutes for questions. If you don't have questions, I do have some, so I would like to. Yeah, so I'm curious about 2 things. One is code coverage. Do you have? Are you measuring code coverage? So I am not asking this like, oh, you should measure code coverage, right? But when you were giving the talk, I just thought that there is an interesting relation between code coverage and a measure, right? The probability measures on events that are interesting, right? It kind of, the code induces a measure, and random, you can talk of randomly differently in there. So I was wondering if you do some code coverage on that.
Yes, so not in this paper. So actually, Jean, we have another one guy that is in the here. He's listening. I don't know if he's available. Maybe so Jean was working with us later to work on an extension of this. So we have 2 extensions. But the second extension that we're working on, it's still work in progress, is to use code coverage as an indicator of how well your fuzzer is. So to guide the fuzzer to go towards directions that it hasn't covered yet. Yeah, so we're working on that. What I can say is that it helps a bit, but it's not evident sometimes, because some of the code coverage by itself cannot actually. So it's difficult to guide the coverage to guide the fuzzer by the coverage in the garbage collector, because some of the things require, for example, it depends on the charge. Yeah, so you need, for example, to reach some parts of the garbage collector, you need maybe hundreds or thousands of objects allocated. Yeah, for example, you need to fill the remember sets, and to fill the remember set, you need or a small remember set or a lot of objects in the remember set. Otherwise, you will never hit the place where the remember set is actually grown. And so I think that the coverage, it helps us there, but it's not enough. So we have to still do some stuff in there. So it's not easy.
Thank you. So is there any other question?
So yes, I have a question. So how much do you think it helped to have this random selection with under some constraints, let's call them? It was just a way to generate enough cases, or do you think that the randomness itself helps in detecting the bugs?
I think that the randomness helps to detect scenarios that the developer doesn't come that doesn't think about. Yeah, because we are so much in there doing it that we think, yeah, this is working, this is okay, and then we test and we write, maybe we'll write 100 tests, but those 100 tests are not, maybe they're covering some similar stuff and they are not covering that bug because we didn't think about that. So the randomness adds some spices, so those spices that maybe helps us hitting the bug. Yeah. In any case, I think that the solution, you have the randomness that plays a part that is important, but without the test reduction, at least not in these bugs that we found, without the test reduction, the solution wouldn't be so nice, because actually instantiating hundreds of objects it's still very complicated to understand what is the layout of the memory and why did I hit this bug in here. So when we reduce that to 5 events, that made the bug super clear. It's not clear to me that actually will happen with any bug. Actually, we have one bug that we let this run for 7 hours in one experiment, and we hit one bug that cannot be reduced. And actually, maybe reducing it takes, I made the math, so I couldn't reduce it after 1 week of reducing. So maybe if you make the math, maybe it takes 1 year or 2 to reduce a bit, if it helps. So maybe there are some bugs that are actually harder to debug and to hit. So but the randomness helped us to go there.
Okay, you then also answered my second question, which was toward the effectiveness of reduction. I mean, in most cases, it was very effective, but there are some instances where the reduction is not enough.
Yes, I don't know if you see it now in the screen. So I put some spoilers from the follow-up paper, where we ran three different fuzzers. Yeah, so we have the ephemerons one that we have in this paper, and then we wrote 2 other ones that were targeting strange allocations, strange allocation patterns, and allocation patterns that actually are that are meant to stress the compaction algorithm. And you see that this is after reduction, I think. No, this is the average events to hit a bug. So it's this. I didn't put the reduction one. I'm sorry. So, but still, we are in the order of some hundreds of events. Yeah, so it's still manageable. So I have the graphic. I forgot to put it on how the reduction actually worked on this. They show, so the reduction on the bugs that we found showed effective, not as effective as in the cases for the ephemerons. Could be that the ephemeron bugs were actually much simpler, and that's all. But the question also would be, how can I change the fuzzing so the events actually are maybe more granular? So it's another way to reduce. So instead of actually trying to have less events, I can make the events larger. I don't know. So instead of allocating a lot of small objects, I allocate some big objects. And how can you make the fuzzer actually understand that to make it easier to debug? I don't know.
Okay, thanks.